All right, so this is what we learned so far, that if you have a trajectory of a moving particle, then the derivative gives you the velocity, which in geometrical viewpoint, it's a tangent vector. And therefore, if you want the unit tangent vector, you would take the velocity vector and normalize it. You divide it by its size. And then for the n vector, you would take the t vector, differentiate it, and normalize it again. Now from this, let's do one more thing. In addition to this, what would you get if you differentiate v? You get the acceleration. Okay. So from this, I want to give you some physical insights into what acceleration does. So first, take this one and solve for v. So you multiply this to the other side, and you get norm of v t times d is v of t. And this one, you multiply this to the other side, and you get norm of t at prime of t times nt equals to t. And those are the things that I'm going to use. So watch. I first take this and differentiate. Now, v prime is what you get on one side, right? V prime. On the other side, you have to use the product rule, right? I noted that any kind of operation that satisfies a distributed property would imply that you have the product rule when you differentiate. And this is a scalar times a vector. So this multiplication is a scalar multiplication. It's taking a scalar and multiplying to a vector. Okay? But scalar multiplication also satisfies a distributed property, and therefore, when you differentiate this side, you should be using the product rule. Okay? So let's apply the product rule on here, which means you differentiate the first and then multiply the second, plus you leave the first unchanged, and then you differentiate the second. That's the product rule, right? Okay. Now, then I'm going to use these two. First, v prime of t is at. Right? So we have on the left side, it's at, the acceleration. And then on the right side, I have t prime equal to this much. So I'm going to replace that. Okay, so I have vt times t prime of t times n of t. Okay. So we get that equation, which looks too complicated to mean. It may seem that it's too complicated to mean anything, but it actually holds some very valuable information.
You're doing the same thing to what you did at the top, right?
Hmm?
You did the same thing that you did at the top. You just differentiated it and then you could differentiate.
No. First I differentiated. This one I differentiated, right?
Yeah.
And then I plug these two in.
Plug those. Okay.
Yeah. So v prime is a, so I replace the left side by a.
Okay.
and I replace t prime by this thing. That's
Okay.
what I got, okay? I mean, you don't have to remember the proof or anything. This is just for demonstration purposes. If you can understand what's going on, that's good enough. Okay? So I'm going to call these separately as AT and AN. Okay. Now, where does this name come from? Well, because this is acceleration, and it's basically saying that acceleration comes in two components. There's one component which is aligned to the tangential direction, and that I'm going to call it as the tangential acceleration. Okay? And then there's another one which is in the direction of the normal direction, and that one I'm going to call as acceleration in the normal direction. So that's a normal component of the acceleration. That's the tangential component of the acceleration. That's the first thing that you can say. So that's why this principal normal unit vector is important. And let's think about what that means. If you have RT, that's a trajectory, right? Some kind of trajectory. And let's draw a three-dimensional curve, not two-dimensional. Let's try something like this. It's a three-dimensional curve, and if you have a point, there's the unit tangent vector, and there's the principal unit normal vector. Okay. What this formula is saying is that in three-dimensional plane, this T and N gives you a plane, right? In the three-dimensional space, T and N gives you a plane, right? And acceleration lies on the plane given by the tangential and the principal unit normal vector. It doesn't have any other components. So that's like the first surprising fact, that acceleration doesn't come outside in some totally different direction. It only has two components, one in the tangential direction, another in the principal unit normal direction. Okay. So that's the first surprising thing. And then the second thing is that they have separate purposes. So first, look at this. That's the rate of change of the magnitude of velocity, right? What's the magnitude of velocity called? If you have if you have velocity and if you take the magnitude, what's that called? That's called speed, right? Speed is the scalar version of the velocity, right? Speed doesn't have the direction information. It only has the magnitude information. It just takes the magnitude information from the velocity, right? And now, what does derivative mean? It's the rate of change. So basically what it's saying is that acceleration in the tangential component is the rate of change of the speed. In other words, think about it this way. If AT is positive, this will be positive, meaning that the speed will increase. Right? It will go faster, okay? And if AT is negative, then it's going to go slower. Okay. So that's what this AT does. It has to do with the particle's change in speed. Okay. If it's positive, it goes faster and faster. If it's negative, it goes slower and slower. Okay. Now that means this AN, the normal component of the acceleration, has nothing to do with slowing down or speeding up. Okay. So let's think about what this would do. Now, remember, because of F equal to ma, you can actually think of acceleration as some kind of force acting in that direction, right? So think about it like this. You have a particle moving, and in the normal principal normal direction, something is yanking it that way, right? What would that result in? If you have a moving particle, and you put some force in one direction, what would happen to the particle?
It'll change direction.
It will change direction. So in other words, AN is responsible for changing directions. Okay. So in terms of the circular motion, what changes the direction? What makes it go in circles?
Acceleration.
Centripetal acceleration, not just the acceleration, centripetal acceleration. Okay? So this is like the centripetal acceleration. So in the case of the circular motion, which is constant speed, if it's constant speed, what's zero? Which one?
Tangential.
Tangential is zero. Okay? Whereas this is positive because it has to be eliminated. So that you can always take an acceleration and find the tangential component and the normal component, and by looking at those values, you can figure out what kind of motion it is. If this is zero and this is some positive value, you know that it's only changing direction, maintaining the speed. Okay? If this is zero and this is positive or negative, what does that mean? What would that mean? If AN is zero,
Straight line.
it'll be going in a straight line, okay? Whereas AT would be change in speed. So you would be, if AT is positive whereas AN is zero, that would be a particle that's speeding up as it's going on a straight line. That's what it means. So that's the reason why we're so interested in the principal unit normal vector and the tangential vector.